Okay. In this talk, we will discuss the order disorder phase boundary in ICE7 and ICE8, which will be investigated by the first principles. My name is Kojiro Moto from this university. So this is a phase diagram of ICE. So as you can see, the phase diagram of ICE is very rich. Up to now, the 50 crystalline phases have been identified experimentally so far. So one of the main reasons of this complex phase diagram is order disorder transition in the hydrogen sublattice. Among these 16 crystalline phases, between ICE1H11 and this, there are 6 hydrogen order disorder transition. So therefore, in order to understand the phase diagram of ICE, the order disorder transition in ICE is very important. But experimentally, most of them, the order disorder transition occurs very at low temperature. So therefore, it's very difficult to investigate experimentally and theoretically. But among them, between ICE7 and ICE8, this order disorder phase boundary has been confined experimentally in very wide pressure range. So therefore, it's very good target to be investigated by the first principles calculation. Previously, in 2004, the phase diagram of ICE was investigated by using the TIP4P model potential, in which the water molecules are treated as a rigid molecule. So at low pressure regions, the phase boundary of ICE was well reproduced by this model potential. But however, between ICE7 and ICE8, the phase boundary was predicted to have a positive Clapeyron slope. This is completely opposite to the experimental result. That is, in experiment, the phase boundary between ICE7 and ICE8 has a negative Clapeyron slope. But this model potential predicts a positive Clapeyron slope. So therefore, at the high pressure region, we must deal with the ICE by first principles. So in this talk, I will investigate the phase boundary between ICE7 and ICE8 by first principles. So this is the atomic structure of ICE8 and ICE7. So as you can see, both ICE8 and ICE7 consist of 2 interpolating hydrogen bond networks. So in this figure, each hydrogen bond networks are represented by the red water molecules and the blue water molecules. They are not connected to each other. So therefore, the ICE8 and ICE7 can be seen as a self-clathrate structure of ICE1C cubic ice. So ICE7 is a hydrogen disordered and paraelectric, and ICE8 is a hydrogen ordered and anti-ferroelectric. So by the order disorder transition, the symmetry reduces from cubic to tetragonal. The ICE7 is a hydrogen disorder, so therefore we must deal with the hydrogen disorder in some way by the first principles. So this figure shows how to deal with this hydrogen disorder. So first, we prepare the 2x2x2 supercell for ICE7, which consists of 16 molecules. Okay? For this supercell, we generate all possible hydrogen configurations which satisfies ICE rule. The number of possible hydrogen configuration is 8100. Among them, only 52 hydrogen configurations are symmetrically distinct. So now we have the 52 hydrogen configurations. Now we have the 52 hydrogen configurations. So from these 52 configurations, with total energy, we can generate a static partition function like this. This partition function can be extended in order to take into account the vibrational contribution within the Coulson-Hamilton approximation like this. This term is a contribution from the zero-point motion, and this term is a contribution from the summary excited phonons. So from this partition function, after we calculate this partition function, we can calculate all thermodynamic quantities. So therefore, in order to investigate the ICE7 and ICE8, what we need are to calculate the total energy and the vibrational density of state for all 52 configurations. After then we can calculate the partition function. So this is our computational method. We use the PB type GGA and True matrix suit potentials. Cutoff plane wave cutoff energy is 100 Rydberg, and the phonon frequencies are calculated by using the density functional perturbation theory. And all calculations were performed by using the called spruce package. Then this is the energy distribution of over the 8100. At the 5 gigapascal, 10 gigapascal, 30, and 50 gigapascal. So as you can see, the ICE8 has the lowest energy. This is the expected result because ICE8 is a stable structure at low temperature. Then as pressure increases, the width of the energy distribution over all configurations decreases. This corresponding to the corresponding to that, as pressure increases, all configurations converge to one structure, that is ICE10. Then now we can calculate the compression curve of ICE7 at 300 Kelvin. Here the solid lines are computational result, and these symbols are the experimental result. And the black solid lines are static result, and the red and blue lines are denote the QHA result for H2 and D2O ice. So as you can see, our calculated compression curve will reproduce the experimental result. So this suggests that our treatment of hydrogen disorder is appropriate for ICE7. At low pressure region, the agreement is excellent, but at high pressure region, our compression curve a little bit overestimates the volume than the experiment. So this is because we are neglecting the tunneling effect, which is important at high pressure. And we found the interesting vibrational effect of the vibrational effect at high temperature. That is, with the vibrational effect, the volume decreases from the static volume. So this is the important result by the zero-point motion. The next is the order disorder transition. The order disorder transition can be captured by the peak position of the heat capacity. This is the heat capacity of ICE1H and ICE11. So at this peak, this peak position corresponding to the phase transition between ICE1H and ICE11 hydrogen order disorder transition. In the similar way, we calculate the heat capacity for the ICE7, and from this peak position, we can determine the transition temperature. This is the pressure dependence of the heat capacity, calculated heat capacity of ICE7 from 5 gigapascal, 10, 20, 30, 40, 50, 60, and 70 gigapascal. So as you can see, the peak temperature of the heat capacity decreases as pressure increases. So from this, we can draw the phase boundary between ICE7 and ICE8. So this is the final result. This solid blue lines are the calculated static phase boundary between ICE7 and ICE8. And the red solid line and dash line denotes the QHA result for the H2O ice and D2O ice. The black lines denotes the experimental result. So as you can see, our calculated result will reproduce a negative Clapeyron slope. Okay, and also in experiment, there is a famous isotope effect. That is, the D2O ice has a higher transition temperature than the H2O ice, and our calculation will reproduce this important isotope effect very naturally. So we have investigated ice. So far we have investigated ICE7, one of the hydrogen disordered form of ice. And we have shown that our calculation will reproduce the pressure volume compression curve of ICE7. And we show the effect of Fallon, and our calculation will reproduce a negative Clapeyron slope and isotope effect. But so therefore, our calculations are qualitatively very good, but quantitatively there are some discrepancy between experiment and calculation. So as you can see, there is a rather discrepancy in TC between experiment and calculation. So therefore, there must be several factors to be improved. Now we think there are four points, but 4 points among them, the size of supercell is, I think this is the most important. this is the experimental heat capacity for the IS1H, but this is the calculated heat capacity for the IS7. So as you can see, the experimental heat capacity peak is very sharp, but in our calculation, the heat capacity peak is not sharp at all. So this is the big big problem in our big problem of our size of supercell. So if we increase the supercell, then this peak must be much sharper. And this peak, the full width at the half maximum is over the 100 Kelvin. So this must be improved. And also, if we take a very large supercell, then we can consider the defective IS8, which is almost the same as IS8. This means maybe we have some configurations with energy very close to IS8. So such a configuration must increase the entropy of IS8, which stabilizes IS8 with respect to IS7. Therefore, we want to expand the supercell. Then the problem is the number of possible hydrogen configurations. The number of possible hydrogen configurations is almost scaled as 3/2 to the nth power. Then this is number of molecules, and this is 3/n to the nth power. So this is currently our supercell. So therefore, the number of possible configuration is about 10 to the second or 10 to the third power. But as the number of supercell increases and the number of molecules increases, then the number of possible configurations increases exponentially. So 10 to the if we have the 888 supercell, then the number of configurations becomes 10 to the 200th power. So therefore, it is practically impossible to sample all configurations if we increase the supercell. So therefore, the solution may be the sampling as many configurations as possible until we achieve the convergence. So therefore, we must calculate the total energy for as many configurations as possible. I don't know how many configurations is necessary for that convergence, but this could be the 100, 1,000, or 10,000, or something like that. So in order to perform such calculation, such calculation is very difficult by hand. So therefore, we need to use some automatic calculations, such as VLab. Maybe VLab will be explained tomorrow by Renato or Pedro. The next improvement factor is exchange correlation factor. Previously, Professor Tura showed that MetaGGA works well for the many systems. The PB has some problem that to describe the intermolecular bond lengths and binding energy of the hydrogen bond. So therefore, if we use a better exchange correlation factor, for example, the Minnesota 06L, then this energy distribution should be improved. This means that our calculation should be improved. This alphonic effector and tunneling effector should be important, but at a very high pressure. But anyway, we must improve this problem of supercell. This requires very computational power. Okay, thank you very much.
I might just mention we actually discussed this, but just sort of for the general audience, that I'll talk very briefly about these sort of cluster expansion techniques, which are kind of ways of mapping these order-disorder problems onto a simplified Hamiltonian for doing thermodynamics, which is a nice tool, I think, for a lot of types of applications, and might be a great one for this, too, if the brute force just doesn't converge quickly enough.
The MetaGGA M06, is it going to be available through Quantum Espresso to the general public?
Yep.
And is there any timeline estimation when it will be available? Oh, really? Okay, great.
It's going to be MO6-L? It's going to be the local version?
MetaGGA, yes.
Okay, so let's move.